All right, let's jump right in. We're going to go on a little journey, one that happens trillions of times a day in the blink of an eye. And it all kicks off with something as simple as a click. Today, we are going deep to uncover the secret life of a database query.
Okay, so picture this. You're at the airport gate, right? And the gate agent needs to pull up the passenger list for your flight. They just click a button on their screen, and poof, there it is. Seems totally simple, doesn't it?
But hang on a second. Let's actually think about what's going on under the hood. That one little click sends a request flying into this massive system that's holding literally billions of flight records. And somehow, the exact list you need just appears. Almost instantly. I mean, how on earth is that even possible?
All right, let's find out. To really get what's happening, we need a map. Now, I know what you're thinking. This looks kind of complicated, but don't worry about it. This is basically the blueprint of a database. And we're just going to follow our little query on its journey, step by step, as it travels through what you can think of as a bustling digital city. So our query's journey starts the second it shows up at the database's front door. This first stop is called the Client Communications Manager. You can pretty much think of it as the system's main reception desk. It's the one that checks the query's ID, makes sure it has the right credentials, and sets up a secure connection before letting it inside.
Okay, so it's cleared security. Now the query gets handed off to the process manager. In our digital city analogy, this is like central dispatch or the main traffic controller. Its big job is to assign a worker, which is just a little slice of the computer's brainpower, to handle our specific request. But it's not quite as simple as just pointing and saying, hey, you, go do this. Because you got to remember, our query is not alone, not even close. At any given second, thousands, maybe even millions of other requests are flooding into the system all at once. It's chaos. So the real challenge here is managing all of that without the whole thing just grinding to a complete stop. So how does it do it? Well, it all comes down to something called a process model. And that's just a fancy term for the database's master strategy, its game plan for organizing all its workers to handle all those requests coming in at the same time. And as you might guess, there are a few different ways to pull this off.
Okay, so approach number one is the most basic. It's called process per worker. Imagine that for every single person who connects, the system builds them their own personal, dedicated workshop. It's really simple and super secure, but man, it's also incredibly wasteful. Building a whole new workshop for every single task, it's just way too resource heavy. It absolutely does not scale.
So that leads us to model number 2, thread per worker. And this one basically solves that scaling problem. Instead of a whole new workshop, now you have one giant office building. That's the single server process. And for each new connection, it just assigns a lightweight thread, which is kind of like giving them a cubicle. It's so much more efficient. And honestly, this idea was a huge breakthrough that really made the scale of the modern internet possible. And then, of course, there's a third option, kind of a hybrid model. This is where you have a pool of workers just waiting around, ready to go. Think of it like a taxi stand. A new request comes in, that's the passenger, and the next available taxi in line grabs it, does the job, drops them off, and then heads right back to the stand to wait for the next fare. It's a really flexible, really efficient compromise.
But wait, before any of these workers can actually start their job, there's one last, very important checkpoint. It's called admission control. And honestly, the best way to think about it is like a bouncer at a really popular nightclub. It takes a look at the new query and checks if the club, the system, has enough room, enough memory, and CPU power to let it in without making things too crowded and slowing everything down for everyone else. If the club's at capacity, sorry, the queue has to wait in line. This is absolutely critical to stop the whole system from getting overwhelmed and just crashing. All right, our query made it past the bouncer. It's in the club. But right now, it's still just a raw request. It doesn't know where to go. It needs a plan, a detailed map to find the exact piece of data it's looking for. So, our query, now with its assigned worker, heads over to the next department, the relational query processor. Now, if the process manager was the city's central dispatch, this part is the master city planner. Its entire job is to look at our simple request, get me the passenger list, and figure out the absolute fastest, most efficient route through the entire city to get that information.
And this whole planning thing happens in a super fast 4-step pipeline. First, parsing and authorization. This is just checking the grammar of the request and making sure the user is actually allowed to see this data. Next, the query rewrite step. This is cool. It simplifies the request, kind of like a GPS finding clever shortcuts you didn't know about. But step 3, this is where the real magic happens, the optimizer. This thing is the brain of the whole operation. It analyzes thousands, sometimes millions of different possible routes to the data and uses a ton of statistics to pick the one that will be the absolute fastest. Once it's found that perfect path, the final plan is handed off to be executed.
Okay, so now we have a plan, a perfect optimized map. Our query is finally ready to actually go get the data. It's time to head down to the vault.
So that execution plan we just made, it sends its instructions deep, deep down into the system to a place called the Transactional Storage Manager. This is the city's vast, super secure public records archive. This is the vault. It's where all the data physically lives, on disk, and it's protected by a very, very strict set of rules. And these rules are so important they have a name, the ACID properties. You can think of them as 4 sacred promises that the database makes. A is for atomicity. It's all or nothing. The whole transaction completes or none of it does. No half measures. C is for consistency. The data will always be valid and correct. No corruption. I is for isolation. This means that even with thousands of things happening at once, they won't interfere with each other or mess up each other's data. And finally, D for durability. Once a transaction is committed, it is permanent. It's saved for good, even if the entire system loses power a second later. So what we've seen so far is how a single query runs inside a single machine. But that's just one building, right? What happens when our digital city needs to expand into a massive global metropolis? I mean, how does a database system scale up from handling a single flight to managing the data for an entire airline or even a giant global bank? Well, the answer is, at some point, you stop trying to build one single, bigger, more powerful computer, and you start building an army of them. This is the whole world of parallel architectures, getting lots of computers to work together as a team on the same problem.
And there are really 2 main ways to do this. On the one hand, you've got shared memory. Think of this as one giant server with multiple processors, multiple brains, that all share one big pool of memory and one central library of disks. It's super fast because everything's right there, but you eventually hit a physical limit. You can only stuff so many brains into one box. On the other hand, you have shared nothing. This is totally different. Here, you have a whole cluster of independent computers. Each one has its own brain and its own library. They share nothing. This setup can scale almost infinitely. You just keep adding more computers. But the challenge is getting them all to coordinate and talk to each other perfectly over the network, which can get really complex.
And that brings us to a really popular third way, kind of a middle ground, called shared disk. In this model, you have a bunch of independent computers, and each one has its own brain, its own memory. But, and here's the key, they all connect to and share a central library of disks. This gives you a fantastic blend of high performance and availability, and it's often a lot easier to manage than a pure shared nothing system. Okay, so our query has successfully navigated the entire digital city. It got a worker, it drew up a perfect map, and it retrieved the precious data from the vault. Now there's only one thing left to do. It's time to head home.
The data it found now travels all the way back up through all those layers we just saw, from the storage manager back to the executor, which puts it all together into a neat little package, and then back to the communications manager at the front door. Finally, it's zipped back across the network, and that passenger list pops up on the gate agent's screen. The whole incredible journey over in a fraction of a second.
And there you have it, the secret life of a database query. From one single click to a mind-bogglingly complex journey through a digital city and all the way back again, literally in the blink of an eye. It's this beautiful, intricate dance of software that powers so much of our modern world. And it really leaves you with a big question, doesn't it? As the amount of data in the world just keeps growing exponentially, what on earth will the next generation of these digital metropolises even look like?